All right, so let's get a start on this electricity stuff. A lot of the stuff we're going to be seeing for electrical circuits is going to look almost exactly like some of the, or at least pretty similar to the stuff we've been seeing with fluid flow. It follows very similar patterns. Of course, it's different physical phenomena, but since it follows similar patterns, we can use similar equations to model it. If you have, for instance, some section of wire, and we usually draw a wire as a straight line, even if it's not actually physically a straight line, no matter what shape the wire is. If you just got some wire bent in any shape, we usually draw it as a straight line for simplicity on the diagram. And these dots at the ends represent ends that could be connected to other things. We're saying that it's not just this wire. This end might be connected to more stuff. This end might be connected to more stuff. We're just looking at one piece of possibly a much larger and more complicated circuit. So if you've got a wire, what is flowing through it? What is actually moving around in the wire that we call electrical circuit or electrical current? Yeah, we've got these charged particles moving. Physically, what's actually moving is, yeah, specifically the electrons. But we don't really care about like how many electrons. We don't care which individual electron moves where or in which direction or how far. We just care about the charge the electrons carry. Each electron has a certain amount of charge. And without worrying too much about the individual electrons, we can say that overall charge is moving in one direction through the current, through the wire. And the current, the electrical current, is the flow of that charge. Electrical current is the flow of charge. And specifically positive charge. Electrons carry charge that we call negative. So if electrons are moving in one direction, we say that the current is actually in the other direction. Like electrons moving to the left means current is flowing to the right, because negative charge moving in one direction can be treated as positive charge moving in the other direction. But in general, when we're talking about current, we assume that it's positive charge, even if it's actually negative charge moving in the other direction. But mathematically, it's the same thing. So you've got the flow of charge across the wire from one point to the other. And we can define current in very much the same way that we do for fluid flow. We're going to define it as a rate of change, change in something over change in time. For fluid flow, we would measure how much volume per time, number of cubic meters of fluid per second. For electrical flow, we don't want to care about how much, like how many cubic centimeters of electrons or something. So we just say change in charge over change in time. And that's the symbol we're generally going to use for charge. Sometimes capital Q, sometimes lowercase q. I've seen both. But this is how we define current. Electrical current is how much charge divided by how much time, in the sense of how much charge moves past this point on the wire per second. And the units for that, what are the usual units of measurement for charge? How would you describe how much charge? Yeah, this is a unit of measurement called coulombs, written as a capital C. One coulomb is a specific amount of charge, and you could think of that as the charge of a certain very large number of electrons. But again, we don't really care about the individual electrons. We're just going to measure a batch of charge called a coulomb. And then time, as usual, is measured in seconds. So that means current is measured in coulombs per second. And coulombs per second is abbreviated as amperes, written as a capital A. So this is the unit of current. Electrical current is measured in amperes, often just read as amps. 1 amp or 1 ampere means 1 coulomb of charge flowing past that point per second. So that's the official unit of measurement for current, amps or amperes. Any questions on that so far? Now let's take a moment to compare this to fluid flow. If you've got a pipe and you've got fluid current flowing through this pipe, why would you expect that to be flowing in that direction? What usually causes fluid to flow from one point to another in a pipe? If you just got this level pipe, assuming you've got no change in height, no change in cross-sectional area, just a simple pipe, what would be causing fluid to flow from one end to the other? Yeah, presumably there's a pressure difference. And we would expect the fluid to flow from where to where? Yeah, from a high pressure to a low pressure. Or more broadly, from a high total energy density to a low total energy density. Maybe there's also height involved, or maybe there's some cross-sectional area changes involved. But in general, from the high total energy density zone towards the low total energy density zone. And the equation that governs that would be a simplified version of the Bernoulli equation. In fact, from here to here, what would be the only parts of the Bernoulli equation we would need? Yeah, we would just need delta pressure. And then on the other side, what would we have? Right, just the negative IR. Because there's definitely current flowing, and presumably this pipe has some resistance. Maybe just a little bit of resistance if it's very smooth, but any pipe is going to have some resistance. So this would be the simplified Bernoulli equation for this pipe. This is just saying that a difference in pressure is what's causing fluid to flow, or to put it another way, fluid flowing through resistance causes a drop in pressure. And the fluid is going to flow, the current is going to flow from the high pressure zone towards the low pressure zone. And the more difference in pressure there is, the faster current is going to flow, with the more resistance causing slower current. We can set up something very similar here. Electrical current is going to flow from a high something zone to a low something zone, but pressure isn't really it anymore. What's the electrical version of pressure? What difference causes current to flow in a wire? Yeah, the electrical potential, or the voltage. If we've got a high voltage zone at one side of the wire and a low voltage zone at the other side of the wire, electrical current is going to flow from high voltage to low voltage. And this is assuming that the wire itself has some resistance, electrical resistance rather than fluid resistance. So we generally denote that by drawing a zigzag in the wire. And we call that a resistor. So a resistor is a circuit element that, essentially it's any circuit element that in certain predictable ways converts electrical energy into something else, some other form of energy. For instance, a light bulb is a resistor. A light bulb converts the electrical energy into light and heat leaving the system. A motor could be treated as a resistor. It's turning the electrical energy into work and heat leaving the system, or kinetic energy and thermal energy leaving the system. Buzzer could be treated as a resistor. It's converting the electrical energy into sound energy and heat leaving the system. Typically, a resistor is going to convert electrical energy into at least heat, maybe just heat, and also possibly some other form of energy leaving the system. But it's going to behave in a very similar way to the fluid circuit, the fluid resistance. you've got a change in whatever is pushing the current through equals negative current times resistance. So this is going to follow the exact same principle, the exact same mathematical pattern. But instead of pressure, we're going to have a difference in voltage. So the difference in this quantity called voltage is what causes current to flow. Current's going to flow from the high voltage zone towards the low voltage zone. The more resistance there is, the less current there's going to be, because resistance represents the level of difficulty to get through this section of wire. And the more voltage difference there is, the faster the current's going to be. And as before, this negative sign just means voltage is decreasing in the direction current is flowing. Or to put it another way, current flows from the high voltage zone towards the low voltage zone. Any questions on that so far? And one other thing I want to emphasize about voltage is that voltage is also an energy density. We've been looking at all these forms of energy density for fluid flow in terms of energy over volume. And we can do something very similar for electrical flow. For fluid flow, we deal with energy over volume as the push that causes fluid to flow, the energy density. For electrical flow, instead of energy over volume, we define energy density as energy over, what's a good way to measure, or how would we describe how much electricity? We don't want to talk about the volume of these electrons. What do we use instead? Yeah, again, we're using charge. So instead of defining energy density as energy over volume like we did for fluid flow, in electrical flow, we're going to be defining energy density as energy over charge. And we call that voltage. Or more formally, it's the electrical potential, as somebody mentioned earlier. So electrical potential is the formal name for this. It's also usually called voltage because it's measured in volts. So the units of measurement for this is volts. And because it's defined as energy over charge, that's equal to joules per coulomb. So 1 volt means 1 joule per coulomb. And you can think of that as like if this resistor involves a voltage difference of 1 volt, that means each coulomb of charge that passes through it loses 1 joule of energy. So 1 volt means 1 joule of energy per coulomb of electrons. Any questions on those definitions so far? And one more thing on the units of measurement here. The voltage is measured in volts. Current is going to be measured in amps. So what does resistance have to be measured in order for this to work out? Yeah, in order for this to fit together, resistance has to be measured in volts per amp. And we abbreviate that as ohms. So volts per amp is abbreviated as the capital omega, read as ohms. So this is the unit of measurement for resistance. You describe a resistor in terms of how many ohms of resistance it has. So more ohms means more difficult to get through. Fewer ohms means easier for current to get through. And related, this equation here is called Ohm's Law. So Ohm's Law is that the difference in voltage between one end of a resistor and another equals negative current times resistance. And ohms is also the unit of measurement for resistance. Any questions on that so far? So a resistor, much like a pipe with resistance makes it difficult for current to flow through. It requires some voltage difference in order for current to flow at all. If there's no voltage difference on a resistor, you get no current flowing. In fact, that's an important thing to watch for. And in any situation where you can establish, if you can establish that the voltage on one end of the resistor and the voltage on the other end of the resistor are the same, then you immediately know there's no current in that resistor at all. No voltage difference on a resistor means no current. But what provides this voltage difference in the first place? What would you presumably want to attach to this resistor to make current flow, to provide this voltage difference? Yeah, a battery. The battery is basically behaving like the pump did in fluid flow. For fluids, if you want current to flow through this pipe, you would presumably make a loop with a pump in it. The pump provides a boost in pressure that causes the current to flow. Likewise, a battery, if you make a loop, battery is usually written as alternating long and short parallel bars. Typically, the long bar represents the positive terminal and the short bar represents the negative terminal. Sometimes those will be marked, sometimes they won't. But generally, the long bar side means the positive terminal on the battery. So a battery is going to provide a boost in voltage. The battery is the reason why there's high voltage on one side and low voltage on the other side. And specifically, the positive terminal, the long bar on the diagram, represents the high voltage side. The negative terminal of the battery, which is the short bar on the diagram, represents the low voltage side. So the battery is using a chemical reaction going on inside its casing to cause this difference in voltage. And that difference in voltage can cause current to flow through other parts of the circuit. But that's really all a battery does. A battery just provides a boost in voltage. And typically the way that is written is another simple equation. Delta V for a resistor is negative IR. Delta V for a battery is just a positive constant, usually written as plus epsilon or plus curve E. And that E is often read as electromotive force. Personally, I think it should be more read as electromotive pressure because it acts more like pressure than force. But it's just an old word for the delta V boost provided by the battery. And all this is really saying is the battery provides a boost in voltage and it's a constant amount. The amount of drop in voltage from a resistor depends on how fast the current is flowing. It varies with I. But the amount of voltage provided by the battery should be a constant. If that battery says 9 volts on the side, it should provide 9 volts of boost all the time. So this is just going to be some constant number associated with that battery. Any questions on that so far? And another important delta V to keep in mind is delta V of just wire. If you're just going through a section of wire with presumably no resistance, and of course any wire has some resistance, there's no such thing as a zero resistance wire. But if you've got a wire with very, very low resistance, what would you assume about, for instance, the voltage at this point and the voltage at this point? If you've got 2 points that are connected by just wire, yeah, they're going to be the same voltage. So we can say that the difference in voltage along just wire is always going to be 0. If there's no resistance, then it doesn't matter how fast the current is flowing, the difference in voltage is 0. Any questions on that so far? So let's try putting those together and actually analyzing this circuit. And let me throw in some actual numbers. If this is, let's say, a 9-volt battery, and let's say we have a resistor whose resistance is 5 ohms. then we should be able to figure out, well, first of all, before we even run any numbers, how many different values would you expect current to have here? How many different currents would you expect in this loop? Yeah, we should expect just one. And this is very similar to the continuity principle for fluid flow. The idea that if you just got one path, there's only one current. The current should be everywhere or the same everywhere along that path. So we're presumably going to have current from the positive terminal, which is a high voltage zone, to the negative terminal, which is a low voltage zone. In fact, it's not just this positive terminal, it's this entire region is going to be a high voltage zone. And this entire region connected to the negative terminal is going to be a low voltage zone. Because again, if you're just going through a wire, there's no change in voltage. So all these locations are at the same low voltage, all these locations are at the same high voltage. And we should expect current to flow through the resistor from the high voltage zone towards the low voltage zone. Since we only have one path, we've got the same current flowing all the way around the entire loop. So just one single value for current. And we can write out what's usually called the loop rule or Kirchhoff's voltage rule. Kirchhoff's voltage law or the loop rule, which basically just says if you start at some location, any location in the circuit, and you travel along some path and you complete a loop, you end up at the same starting point. Doesn't really matter which loop. In many circuits, there may be several different loops you could go through. But if you start and end at the same point, what does that tell you about the voltages? What exactly is going to be zero? Yeah, the change in voltage is going to be zero. The change in voltage, or rather the sum of all the changes in voltage around a complete loop, has to add up to zero. As long as you're starting and ending at the same point, all of the delta voltages you encounter have to add up to zero. In this particular context, you start here, you go through a battery, and you go through a resistor, and you get back to the starting point. So in this context, you add up the delta voltages. You got a delta voltage from a battery, you got a delta voltage from a resistor. Everything else is just wire. So those have to add up to zero because you get back to the starting point. Then you can fill in the delta V for each one of those. Delta V for a battery is plus epsilon. Delta V for a resistor is negative IR. We know the epsilon for the battery, 9 volts. We know the R for the resistor is 5 ohms. So current is the only unknown left. And before we even plug in any numbers, how would you isolate current here? Yeah, if we just add IR to both sides, divide by R, we get current equals epsilon or E over R. And this tells us a couple of important things. A stronger battery leads to faster current. A more resistant resistor leads to slower current. And that's what we should expect. If you want more current, you would plug in a stronger battery or use an easier resistor. And now we can actually fill in those values. We plug in 9 volts for epsilon, divide by 5 ohms for the resistance. 9 over 5 would be 9/5 or 1 4/5, so 1.8. And what's volts over ohms? Yeah, that should just be amps. Because remember, ohms can always be replaced with volts over amps. Volts and volts cancel out, divided by amps become just amps. So that will be the current, and not only the current in the resistor, but the current throughout the entire loop here. So current equals 1.8 amps. Any questions on that circuit? All right, then let's try a more complicated circuit and see what we can do with that. All right, let's say we have these resistors. So we've got a 12-volt battery, a 3-ohm resistor, and a 6-ohm resistor. How many different currents would you expect to see in this circuit? Two different currents? Because we're gonna have, I usually like to start analyzing currents from the battery. If you got current going through the battery, presumably you got a positive terminal and a negative terminal. So this is a high voltage zone. And this is a low voltage zone. Presumably you're going to get current going from the high voltage zone around the circuit towards the low voltage zone. The thing is though, as soon as this current hits this junction, what's going to happen? Yeah, the current's going to split. We've got two different paths the current could take. Current could go from the positive terminal outwards and then take this path and then get back to the negative terminal. Or current could go through from the positive terminal and then take this path and then back to the negative terminal. So the current has two different paths it can take. And that means I think we're actually going to get three currents here. You've got the current through the battery. Let's call that I sub 0. You've got the current through resistor 1. Let's call that I sub 1. And you've got the current through resistor 2. Let's call that I sub 2. So we've got possibly different currents through each resistor, and we've also got the current through the battery itself. So possibly three different currents here. And we can still use Kirchhoff's voltage law. We're just gonna have to be careful about how we set up loops, because there's not just one loop here, there's several loops. And we can also use Kirchhoff's current law, which tells us something about what's happening at the junctions. The current law, or the junction rule, is talking about what's going on at a junction, at a point where several wires come together. For instance, here. What do we know? Like, for instance, it looks like here we zoom in on that. We've got current 2. We've got current 1. And we've got current 0. So what should we assume about these three values? Based on that junction. If these were pipes, what would you say about these fluid currents? Yeah, the current 0, the current flowing out, has to equal current 1 plus current 2, the current flowing in. And that's generally true for any location in the pipe or wire. It works the same for pipes and wires. Any single location, especially locations where several wires come together, but really any location or any region. If you just draw some blob-shaped region, the total amount of current flowing into that region has to equal the total amount of current flowing out of that region. We shouldn't expect charge to accumulate in some region. So for any location, or region, the sum of all the current flowing in has to equal the sum of all current flowing out. Or sometimes we just lump them all together and say the sum of all the currents has to add up to 0, treating current flowing in as positive and treating current flowing out as negative. But I usually find it easier to just set it up as the total of all the currents flowing in has to equal the total of all the currents flowing out. Any questions on that so far? So we know current 1 plus current 2 has to match current 0. Now let's see if we can apply Kirchhoff's loop rule, the voltage law. And these are, by the way, the main concepts we're going to be using throughout all of circuit analysis. These two ideas, plus the concept of delta V for each one of those types of things. Delta V for a battery equals plus epsilon. Delta V for a resistor equals negative IR. And the fact that a wire has no voltage difference. This is pretty much the entirety of concepts we're going to be using for analyzing circuits. Everything else is just this plus a bunch of algebra. Any questions on those concepts so far? So let's try applying these principles to this circuit. From the junction rule, we know that current 0 has to equal current 1 plus current 2, which means if we can find any two of those, we immediately know the third one. To figure out each one individually, though, we're going to have to look at individual loops. So what's one loop we could draw here? If we start, like let's say we start at this corner, we could draw a loop that passes through what things? Like if you just start traveling along some path, what's the first thing you're going to pass through? Yeah, you're going to go through a battery, and then you keep going. What else could you pass through? Maybe R1. You could go through the battery and R1, and then you're back to your starting point. So that is a loop. So for loop 1, let's say this is the top loop. Battery and resistor R1. So if we write out the Kirchhoff's voltage law, the loop rule for that loop, we've got battery and resistor 1. So those delta V's have to add up to 0. Delta V for the battery plus delta V for resistor 1. Note that resistor 2 is not part of that loop, so it's not included in the equation. You're only including things that you pass through on that loop. Those then have to add up to 0. We fill these in with our usual epsilon and our usual negative IR. Specifically I1, R1. We got to label those subscripts because it matters which resistance and which current we're talking about. Solve this for I, and we're going to get the same thing. Add I1, R1 to both sides, divide by R1. You get I1 equals epsilon divided by R1. And we could even fill those in. 12 volts divided by 3 ohms. And we get 4 amps. So we now know the current going through that branch. Any questions on that so far? Then any thoughts on how we could figure out current 2? What's another loop we could draw in? Yeah, if we draw a loop, let's say starting at this same corner, but a loop passing through the battery and resistor 2, that's still a valid loop. It's still a path that starts and ends at the same point as itself. So if we draw out that loop, let's say this is the outer loop, using the battery and resistor 2. Then we could say those delta V's, delta V from the battery and delta V for resistor 2, have to add up to 0. And note that this is going to be fundamentally the same equation. We're going to have a plus epsilon from the battery. We're going to have a negative I2 R2, because it's that current and that resistance, which means this is going to solve in exactly the same way. I2 is going to be epsilon over R2. So we fill in 12 volts for epsilon, divide by R2, which is 6 ohms. And we get 2 amps. So that's the current through resistor 2, 2 amps. Any questions on that so far? And now that we have I1 and I2, we can immediately also find what other information. Yeah, we can find I0. Thanks to the junction law, the idea that the total current flowing into this point has to match the total current flowing out, we can just add I1 plus I2 together and get I0. So 4 amps plus 2 amps is going to be 6 amps. Which means in this situation, if we arrange these in this format, we're going to find that the battery has 6 amps of current flowing through. And when those 6 amps of current hit the junction, they split up. You get 4 amps going through the middle wire and 2 amps going through the lower wire. Any questions on that so far? So the current splits up. Another very important question here, though, how much voltage is resistor 1 getting and how much voltage is resistor 2 getting? Why do we use the outer loop to find I2? Specifically because that is a loop that includes that current. If we had just looked at loop 1 does not include resistor 2, so that doesn't really tell us anything about resistor 2. The current preferring to go through the path with least resistance, if you've got a choice of different paths, and we would usually call this a parallel network or parallel branches. If the current is able to split, if one of the paths has less resistance than the other path, then you will generally get more of the current going through the path with less resistance. But note that that doesn't mean the path with more resistance gets no current. The path with more resistance does get some current, it just gets less current. And also note the proportions here. How do these currents compare to each other, the 4 amps and the 2 amps? Yeah, resistor 1 is getting more current. Specifically, how many times more current? Twice as much current. How do the resistances compare? Right, half as much resistance gets twice as much current because they should be inversely proportional. If these two paths, so this path and this path are in parallel with each other, these are two paths that start at the same point and end at the same point. their resistance ratios should be inversely proportional to their current ratios. For instance, this over this, resistance 1 over resistance 2 is 1 to 2. Current 1 over current 2 is 2 to 1. So the ratio of resistances should be the inverse of the ratio of currents. Any other questions on that so far? Now let's take another look at voltage drop. How do you find the voltage drop, the difference in voltage for a resistor? What's the usual formula for delta V for a resistor? Yeah, negative IR. If you now calculate that for each one of these, for the resistor 1, multiply current times resistance, and what do you get? Yeah, negative 12 volts. So this one is getting a voltage drop of minus 12 volts. In other words, this one is getting the full voltage of the battery. What about resistor 2? If you multiply current times resistance, 2 amps or 6 ohms times 2 amps. Yeah, this one is also negative 12 volts. So resistor 1 is getting the full voltage of the battery. Resistor 2 is also getting the full voltage of the battery. Why is that? Why are they both getting the full voltage of the battery? Why don't they have to split up the 12 volts amongst themselves? If we start labeling this, I'm drawing out a somewhat more complicated circuit, just the same idea, but with just more bridges between these two regions. If this has a 12 volt battery with a positive terminal and a negative terminal, let's start labeling voltages. Only connected by wire, right? Yeah, and if they're only connected by wire, what does that tell us about the voltage of all these locations? These ones would actually be called in parallel, and we'll get to the reasons why that is later. But if all these points are connected by just wire, what does that tell you about their voltages? Zero difference. Yeah, they're all the same voltage. So all these points are at the same low voltage versus all of the points on the other side. So this point, like next to the positive terminal, and this point, and this point, and this point, these points, all connected by wire, those are all going to be at the same high voltage. High voltage because it's connected to the positive terminal. And we can even label those. There's not really a universal standard for what a certain value of voltage means. We usually care more about differences in voltage. But what I usually do is whatever the lowest voltage in the system, I usually just call that 0 volts. Specifically, whatever is connected to the negative terminal of the battery, we're going to just call this 0 volts, which means this is also 0 volts, and this is 0 volts, and this is 0 volts. It's not just that this point is 0 volts. This entire region is a 0 volt region. Then you go through the battery. What can you say about the voltage at this corner? Yeah, this should be 12 volts because the battery provides a boost in voltage. And again, not just this corner, but this entire region is a 12 volt region. That's the same high voltage that all these points are at. So this entire region is 12 volts. This entire region is 0 volts. which means each one of these resistors individually is a bridge from a 12-volt region to a 0-volt region. 12 to 0, 12 to 0, 12 to 0. So each one of these resistors is a path whose delta V is negative 12 volts. In other words, each one of them is getting the same full voltage of the battery. And so if resistors are arranged in this way, if the resistors are arranged in parallel, each one of those parallel paths gets the same full voltage. They don't have to split up the voltage. They all get the same voltage because they're all starting at the same high voltage and they're all ending at the same low voltage. So they all get the same full delta V. But what happens to the current flowing in? If you've got current flowing in, what can you say about the amount of current each one gets? Do they all get the same full current? No, the current has to get split up because current is the flow of charge. If you've got a certain amount of charge moving in, some of the charge goes one way and some of the charge goes the other way. So the current gets split up amongst the available paths, but the voltage, all of them get the same full voltage drop. So anytime you've got resistors arranged in parallel, they all get the same full voltage drop, but they have to split up the available current. And as was mentioned earlier, the one with less resistance is going to get more current. The one with more resistance still gets some current, it just gets less of it proportionally. Any questions on that so far? On the other hand, if the resistors are in series, if you just got like a resistor and another resistor and another resistor, what would you say about the current those are all getting? Yeah, they're all going to get the same current. They all get the same full current. They don't have to split that up because it's just one path. But what do you know about the voltage? If you've got, let's say, a very high voltage on one side, very low voltage on the other side, are they all getting the same full voltage difference? No, because we're going to have to lose some voltage when you go through a resistor. So you get to a, let's say, a kind of high voltage. You go through another resistor, you lose some more voltage. You get to, let's say, a kind of low voltage. And then you lose more voltage and you get to a very low voltage. So if the resistors are in series, if they're all on the same path, one after the other, they all get the same full current, but they have to share the available voltage drop. Whereas if the resistors are in parallel, they all get the same full voltage drop, but they have to split up the available current. That is really the main difference between series versus parallel. If they all have to have the same current because they're all along the same path, then they're in series. If they all have to get the same full voltage drop because they're all starting at the same high voltage and all ending at the same low voltage, then they're in parallel. Any questions on that? All right, then we will look into some more examples next time. Feel free to email me if you have any questions, and I will see you then. You're welcome.